Okay. So again, maybe I have to repeat myself since I'm recording it now. So this is basically what we have discussed so far. We introduced the meaning of a force by writing the in the Cartesian coordinate the vector equation for a force. And we demonstrated if you have several forces, the resultant is simply the sum of the x component of all those forces times I plus the sum of the y component times j. And if the resultant is zero, that means the object, or in this case, the particle, is at rest. That implies that some of the x components and some of the y components have to be zero. And we call these equations of equilibrium. They allow us, if we have a problem with up to two unknown forces, as long as that particle is in equilibrium, to find those two unknowns. So that's in a nutshell what we have discussed so far. Any questions before I move forward? No? Okay. So with that said, what we want to do today is to extend those concepts to three dimension. In other words, instead of having a two-dimensional x, y coordinates and having a force that we demonstrated, if the angle that this force makes with the x-axis is given, we can write this vector equation in these two alternative uh, forms, okay? Uh, cosine of theta I plus sine theta j. We want to know if you have a force in three dimension. Let's say this is a three-dimensional space, x, y, and z coordinates. How does the vector equation and also these other concepts, resultants and equilibrium, then would be in the case of 3D. So with that, let me, more people are joining. All right. So let's say you have a force like F, and you set up the coordinate system so that the origin is along the direction of F. And first of all, the definition of the components of a force acting in space, or the x, y, z components, is this. You can find the components by simply projecting that force along one of these planes. Let's say this plane xz. So projection of the tip of this force on this xz plane is h. Now, if you draw a line perpendicular to z-axis and a line perpendicular to x-axis, or in other words, drawing a line parallel to the two axes, what results here, this is the x component, this is the z component of this force. And if you draw a line parallel to OH, okay, this will be the y component of this force, okay? Now, we introduce some definitions. If, first of all, if you connect this tip to this point here, okay, you can prove that this is a right angle. And the same thing here. If you connect this, this is a right angle, and this is a right angle. So In this triangle, this is the angle that this force is making with the x-axis. And this is the angle that it makes with the z-axis. This is the angle that it makes with y-axis, okay? We call these thetas the directional angles because these angles, if we have them, fully describe the orientation of this force in space. Cosine of these angles are called direction cosine. So we call them direction cosines. So what's the big deal? First of all, knowing from the concept of the resultant that a force is the vector sum of its components, we can simply write F is f of x plus f sub y plus f sub z vectors. But in Cartesian coordinates, we introduce, similar to the 2D, unit vectors along these axes, which we call them I, j, and k. So following the definition of unit vector, we know that f of x as a vector is the magnitude of f of x times I. F sub y is the magnitude of the projection of this along y times j, and f sub z is the magnitude of f of z times k. So the first form of the unit of the vector equation for a force in 3D can be written as f of x times I plus f of y times j plus f of z times k. So this is the vector equation of a force in three-dimensional space. However, we do see from each of these triangles, for instance, if I consider this, and let me call this, for instance, L. So in this triangle, which is like this is L, this is O, okay, this is F. This is what theta x is. And this is what f of x is. So cosine of theta x is simply f of x over f. You can show that similarly, that cosine of theta y is the magnitude of f sub y over the magnitude of f, and cosine of theta z is the magnitude of f of z over f. Therefore, if you substitute these into this equation, that is, for instance, f of x is cosine theta x times f sub y is cosine theta y times f, and so on, you can write that relationship in an alternative form, which is this: cosine theta xi plus cosine theta y j plus cosine theta z k. So if you have the components of the force, you can use this equation. If you have the angles that the force makes with those axes, you can use this equation to describe the force. Remember, however, in 2D, we had only one angle. We needed only one angle to describe the direction of a force. And the relationship between this angle and this angle are clear. Alpha is 90 minus theta. In 3D, the relationship among theta x, theta y, and theta z is not like that. The relationship that exists among these is that we can prove that cosine of theta x squared plus cosine of theta y squared plus cosine of theta z squared is equal to 1. So if you have two of these angles, you can always find the third one. But also remember, if the components are given, cosine theta x is f of x over f, cosine theta y is f of y over f, and so on. Okay? Yet there is a third way of writing the vector equation for a force. And that is, if you have a force, okay, along a direction and the components of coordinates of 2 points along that direction are given, okay? For instance, this is x, y, and z of A are given, x, y, and z coordinates of point B is given. By definition, as we showed the other time, is that we know that the force is the magnitude of the force times the unit vector along the direction of that force. This is also valid in 3D. So if we can write the unit vector equation, we can use this relationship to write the equation for a force. But from calculus or physics and so on, you remember easily that the vector equation for a unit vector along a direction where the 2 points along that direction are given can be simply written as x of b minus x of a times I plus y of b minus y of a times j plus z of b minus z of a times k divided by the length of AB, which is simply the sum, the square of the sum of the squares of these quantities in these parentheses. So this is the vector equation for a unit vector. And therefore, the third alternative form for equation of a force in a space can be simply written like this. So depending on what information you're given, you can write the vector equation for a force using one of these three alternative forms. So we have accomplished something here. And that is, we now have the vector equation of a force in three-dimensional space. Or we have described a force in the Cartesian coordinates in 3D. With that said, so we can extend the two concept of resultants and equilibrium of forces acting on a particle to 3D. The resultant of several forces in space where the vector equation for all those forces can be found using one of these three approaches is simply this. And therefore, similar to 2D, if we can set up the vector equation for the resultant, we can easily show that this comes down to writing the sum of the x component of each force, sum of the y component of each force, and sum of the z component of each force. And this will be the resultant equation in 3D. Concept of equilibrium is similar. If all forces acting on a particle cancel each other, or the particle is not moving, that implies that the resultant is zero, or the components of the resultant is zero, and therefore these will be the equations of equilibrium in space. So with that said, we have all the tools that we need now to look at the equilibrium in space and do a few problems. But let me stop here first, see if you have any questions that I may answer related to what I just discussed. And if not, I will go ahead and do a few problems. Any questions?
I have a quick question about the
Please.
unit vector equation that you just gave us a minute ago.
Mhm.
So would we use that in the third equation there?
Yes, correct. In other words, if you have a force which is only given by 2 points, coordinates of 2 points, this is the equation that you use. In other words, the magnitude of the force that is given times the unit vector, where the unit vector is found using this.
So that's
And
when
I'm
you
going to
have two
demonstrate that.
points.
Exactly, exactly. That's only the case where you have a force described by the coordinates of 2 points given along that direction. I'm going to do some problem, demonstrate the application. Any other questions? If not, let me do a few problems here then. Okay. Okay, so let me start with a few good problems here. Um, I will actually do problem 2.76 in your book because that's a very good uh, problem. So here in this problem, we just simply want to play around with the vector equation for a force and see how we can set up the vector equation for a force. This is the problem, okay? You do have a cable that is attaching this point A along y-axis to a point C here on xz plane. And the problem states that the force is given, a force AC that acts along this direction. And we want, and we are given the uh, magnitude of this force. In other words, the magnitude of this force AC is given as 5,250 pounds. Okay. And, uh, the geometry is of this problem is given. We know the length of AC is 70 feet. And we also know if you project, of course, AC on on plane XZ, which is what OC is, this angle is given 50 degrees. And also this height is given 56 feet. So we want to basically, so these are what's given. What the problem is asking us to find is we want to find the components of F along this three coordinates. This is part A. Part B, problem is asking us to find the angles that this force makes with the three coordinates so that we can write the vector equation for this force in two different ways. Okay. So let's begin, okay? This is how I would solve this problem, okay? First of all, in this triangle, if this angle is theta, okay, I can write the sine of theta is 56 over 70. That will give me theta comes out to be 53 degrees, okay? So therefore, projection of this force along xz, which is this, I call that FOC, can be found because F of OC is the projection of this force along this, which is basically in this triangle, right? You can write the magnitude of FOC would be the magnitude of F times the cosine of that angle theta, which is 53 degrees. So this is given, okay, is 5,250. So if you substitute in this equation, you can find the magnitude of F of OC, and that comes out to be 3,160 pounds. Remember, I said that if you project a force on one of these planes, in this case xz, then from here you draw these lines perpendicular to this axis and perpendicular to this axis. This is your f of x, and this is f sub y. And let's, if I call this, for instance, point H, in this triangle here, okay, okay, in this triangle, which is a right angle triangle, you can easily see that. Maybe if I redraw that in here. In other words, this is that triangle, HCO, and this is F of OC. So you can, and this is F of X. That's what I have drawn in here. So you can easily see that F of X is simply F of OC times this angle, and this angle is given. This is 50 degrees, so this angle is 40 degrees, okay? So this would be F of OC cosine of 40 degrees. Therefore, f of x is going to be 3,160, which is what we found for f of OC, times cosine of 40. So we will be able to find that, and that is 2,421 pounds. So we found the x component of the force. Y component is this. This is the y component, okay, in this triangle. So the y component in this triangle, which is right angle triangle, can be seen easily that it is the, okay, we had this angle, theta, right? 53. So if this is 53, this would be 37 degrees. So f sub y then would be the magnitude of f times the cosine of 37. So we have this 5,250. So we can find f sub y to be
Can't
4,000.
see what you're doing, Professor.
Oh, sorry about that. Would be 4,193 pounds.
We still can't see.
Oh, you can't see it? Let me see. Oh, sorry about that. Here again. So let me actually raise this a little bit so you can see the whole. Yeah, that's better. So that way you can see the whole picture of the whole problems. Okay.
F is the same as FAC, right?
Oh, this one here? No, here I'm talking about in this. Yes, exactly. Sorry about that. Yes, it is FFAC. Yes, correct.
Okay.
Yes. So I better write it down to prevent some confusion. Any other questions? So we found f of x, f of y, and f of x and f of y. Okay. But how about f of z? F of z is this. Oh, I'm sorry. This is, you know what? This is f of z. Okay. So how do you find f of z? Now, if you look at this triangle, again, you have this right angle triangle here. So f of z from this triangle, which let me call that M, and let me draw that here. This is FOC, and this would be F of Z, where this is that 50 degrees. So F of Z would be F of OC again, which is, we found it, 3,160 times the cosine of 50 degrees, and you can find it to be, okay, 2,031 pounds. So this is F sub C. So we solved the first part of the problem, which was asking us to find these components. Now, in the second, any questions?
Could we have solved for f of z just using the triangle that we solved for f of x in and just
Absolutely.
Okay.
Absolutely. Yes, sure. Yes. Any other questions? Okay, so we did the first part. Now, how do you find the direction cosines? It's easy. Why? Because we said that cosine of theta x is f of x divided by magnitude of f. So we have the f of x, 2,421. Magnitude of f is given, 5,250. So that will give me theta x. That comes out to be 66.2 degrees. Same thing with cosine theta y, is the magnitude of f sub y over the magnitude of f. So this is f sub y, 4,193 divided by 5,250. So I can find theta y to be 37 degrees. You can find cosine of theta z the same way, or you can use this relationship, whichever you prefer, okay, plus cosine theta z squared is equal to 1. You have two of them known, you can find a third one, or use cosine theta z, which is f of z, which is 2,031 divided by 5,250. And sorry for the messiness, theta z comes out to be 67.3 degrees. Any questions? No? Okay. So I'm going to do another good problem here. Let's see. I have a few problems here set up. Okay. All right. So this practice was just to find the vector equation. Basically, that's what we did. We saw that if you have a force given in 3D, how you set up the vector equation. What I want to do now, do a second type of problem, and that is, given a set of forces, find the resultant of those forces. And the third problem I will do will be the equilibrium, which we'll probably do on Monday, not today. So to demonstrate a good problem of resultants, this is what I have selected. Problem 289 from your book is a very good problem. And this is sort of the geometry of that problem, okay? You do have a plate like this. This plate is supported at these points A, C, let's see, this is X, this is Y, this is, oh, I'm sorry, X, Y, this is Z, this is Y, and Z, okay? So this plate at point B, which is this corner, and by the way, these dimensions are given. This is, let me actually bring the book because my drawings is not that great. So let me go to the original diagram, problem 289. Okay. Okay, let's see. 289 here. Okay, here is a problem. So you do have, actually, this is a, in fact, this is a pipe system, something like this. So in order to hold this pipe in place, we have attached these two ends to these two lines along X and Y coordinates. We know this side is 0.6 meter, this side is 0.4 meter. And then we have attached a cable. There's a hook here, and a cable, it goes around through this hook and is connected to these two walls at these 2 points, D and E. Okay. The location of these points are given. This is 0.4 meter. This is, I'm not doing a good job as far as the dimension goes. This is 0.21 meters. For D, this height is, okay, 0.51 meters. And this Z is 0.28 meters, okay? All right, so I have A, B, C, O, okay? So this is the problem. So we have a frame or pipe, whatever that is, ABC, that is basically supported partly by this cable, okay? We do know that the force in this cable is given. The force in this cable is given is as 300. In other words, if you look at this cable, is obviously exerting a force like this and a force like this to hold this pipe in place. The magnitude of the force in DBE is given as 385 Newton. Okay. So, in other words, each of these cables, or instead of writing this, is better doing this way, force in BD is equal to the force in BE and is equal to 385 Newton. So this is what has been given, okay? So what we want to know, okay, we want to find the components of this force, one of these forces, which is connecting B to D. That's the first part of the problem. So we just want to write the vector equation for this force. Any questions? So this is a 3D problem, but of a different type. In other words, we want to find f of BD, the equation, vector equation for BD. Okay. In fact, as I'm looking at it, I had changed this problem and made it a more complex. Why I do is, well, that's okay. Let me first do this problem and I'll do the next one. So this is the second or third type of problem that in order to set up the vector equation for a force, all we have been given are the coordinates of 2 points along this force. Of course, these are not given immediately, but you can set them up. In all three problems, so that you don't sort of make unnecessary mistakes, I would suggest that as the step one, you write down the coordinates of all points that are shown in the figure, because you need them. You need the coordinates of these points in order to write the vector equation. So I'm going to write all these down. So this P is on XZ plane, has no Y, is X is given as 0.4, Y is given as 0, and its Z is given as 0.6. This point A is only along Z axis and is 0, 0, 0.6. Point C is only along X axis, so its coordinates 0.4, 0, 0. Point E, okay, which of course for this problem we don't need it, but nevertheless I write that down as 0.21 is on XY plane, so it has no Z. Its Y is 0.4 and 0. Point D is on YZ plane, so it has no X, is Y is given as 0.51 and its Z is given as 0.6. Okay. Once you set that up, then step two is if you want to write the vector equation for BD, let's write that down. This is magnitude of that times the unit vector along BD. Okay? We have been given the magnitude of the force, and all we want to do is to write the vector equation for the force. How do you do that? You need to set up the vector equation for UBD. And UBD would be what? Components of this minus this, each corresponding one. So you write x of this minus x of this, 0 minus 0.4. So you have negative 0.4, I. Y of 0.51 minus 0. So you have 0.51 J. They are 0.6 minus 0.6. Okay. So you have 0. Okay. Plus 0 K divided by the square root of 0.4 squared plus 0.51 squared. Okay. And that's it. Okay, let me make sure that I did it correctly. The coordinates of this, z of this is 0.28. See, I made a mistake here. Point D is x is 0, is y is 0.51, but its z is 0.28. I had not, so this is not 0. Would be 0.28 minus 0.6, which would be negative 0.32K. So this is the unit vector equation for this force, okay? If you simplify that, okay, plus 0.32 squared, okay? If you find this, what is under this square, you'll see this comes out to be roughly 0.7. But anyway, now that you have the unit vector, you can simply write the vector equation, which would be 385 times negative 0.4 I divided, of course, by 0.7. I can factor that out, plus 0.51J minus 0.32K. So, of course, you can perform the multiplication and find out the equation in this form, okay? But that's how you find the vector equation for a force when the 2 points along the direction of that force is given, okay? Any questions? If not, well, we have 4 minutes. At least I can start that, okay? So I would slightly modify this problem, and maybe I would at least start that. If I cannot finish it, we can finish it next time. So I changed this a little bit, the same problem, okay? So we have the same pipe, but I changed a few things here. So we have A, B, C, these points where this pipe is supported, but we do have a cable now going from B to point E, and a cable from B to point D, but the forces in these two cables are different. Force in BD is given as 350 Newton. Force in BE is given as 400 Newton. And this problem, of course, let me give you all these dimensions. This is 0.4. This is given as 0.28. Okay. And this is also given as, I changed it a little bit, 0.28. And this height is 0.51. And this is 0.6 meters. This is 0.4 meters. So the problem statement now is different. What we have is this. We have two cables that are attaching this pipe to these walls. We don't like this sort of a configuration. We want to replace these two cables with a single cable instead that connect B to somewhere. In other words, we want to find the resultant of these two forces. So we want to see how you find the resultant of two forces in a space. Okay. Step one is the same. Write down the coordinates of all these points. So point A, I have 0, 0, 0.6. Point B, I have that 0.48. I'm sorry, this I changed this also, 0.48 also. Made the problem slightly different. So this 0.4800 point, I'm sorry, point C would be 0.4800. Point B would be 0.48, 0.6. Point E, okay, would be 0.21, 0.40, and point D has the coordinates of 0.51 and 0.28. So let me just maybe finish at least I finished the first part, which I called the first step. So you write down the coordinates of all the points, and the next step is you need to write the vector equation for each force BD and BE. Okay, because then once you set these up, you can find the resultant. But how do you do that? Well, you need the unit vectors for each, right? Force of BD would be magnitude of FBD times the unit vector of BD. Okay, this is given. BD is 350. And magnitude of FBE, I mean, vector equation for that would be 400 unit vector along BE. Okay, so we need to set up the vector equation for these. If you don't mind, I'll just spend literally one more minute and I can set up these unit vectors, because unit vector for BD would be what? This minus that. So 0 minus 0.48. So would be negative 48 I. 0.51 minus 0 plus 0.51 J. 0.28 minus 0.6, which is negative 0.32 squared, divided by the square root of this 48 squared plus 0.5 squared plus 0.32 squared. The important thing here, which I want to emphasize, if you are considering the force BD in this direction, okay, remember the unit vector should also be set up in the same direction. And that is important, because if this is acting in a direction, this is the tip, this is the tail. You always subtract the coordinates of the tip from the tail. So be careful, otherwise these signs will not end up to be correct. And I would quickly write down, because I just want to give you the answer for this. If you do U of BE, you'll see that it comes out down to be negative 0.27 I plus 0.4 J minus 0.6 K, and the square root of some of these squares comes out to be 0.77. So by having these, you can simply write the corresponding vector equations. Force in BD E comes out to be negative 140.3 I plus 207.8 J, negative 312 K. Force in BD comes out to be negative 233.3 I plus 243 J minus 155.5 K. So you have the vector equation for these forces. R would be simply sum of each component. So in order to write the vector equation for the resultant, you add up the corresponding components. And if you do that, you end up with negative 373.6I plus 450.9 J minus 467.5 K. And this is the equation for the result. And I'm sorry that I went so quick. At least I wanted to demonstrate the application of the concepts that we discussed, which was introducing the vector equation, how you set up the vector equation for a force when the angles are given or when only 2 points along the force is given, and then how to find the resultant. Sorry about that. Again, for the speed of the coverage, I'm going to stop here and answer any questions that you may have. Any questions?
Hi, I had an unrelated question. It had to do more with the recordings.
Okay, sure.
So I just got added to this class because I was on a wait list, and I
Oh,
was trying
okay.
to see, look at